Okay, welcome everyone. We're doing another deep dive today, and this time we're going straight into the world of Formula One. But maybe not in the way you usually think about it. Forget the drivers, the points battles for a second. We are zeroing in purely on the tech, the hidden side. Our mission really is to get you completely up to speed on F1's, well, its secret technological war. It's more than just racing. It's like the ultimate R&D lab on wheels. The analysis we read put it perfectly. The technological war is fought on a minuscule scale. It's all about tiny gains. You've got teams throwing literally hundreds of millions into research and development every single year. It's this constant, relentless cycle, always adapting to new rules, always chasing that last thousandth of a second, just relentless perfectionism.
Exactly. And what we want to do is break down those massive technological jumps for you. Everything from, the mind-bending aerodynamics and those incredibly complex power units, right through to how they use data, the materials they invent, and crucially show you how all this extreme F1 tech connects directly back to the car you might be driving. Yeah, we're hoping for a few aha moments today. In fact, let's kick off with two facts that just jumped out at us. One, an F1 car makes around 1,500 kilograms of downforce. Think about that enough force to theoretically drive it upside down.
Upside down?
And maybe even crazier. Those engines, the little 1.6-liter turbos, they're hitting over 50% thermal efficiency. That's groundbreaking.
50%, that efficiency number is genuinely hard to grasp for an engine. Okay, let's start with the spade. The aero, that 1,500 kilos of downforce, that doesn't just happen. That's got to be thousands upon thousands of hours shaping every surface, right?
Oh, absolutely. But here's the twist. The most important aero work. It's mostly invisible. We all see the big wings front and rear. But the real magic, over 60% of the total downforce, is generated by the car's floor, the underbody.
60% from the floor, that feels backwards. How does the bottom of the car do that?
It all comes down to something called ground effect. They use these incredibly complex tunnels and diffusers under the car. It was actually banned for ages from the late 70s, but it made this huge comeback with the 2022 rules. Essentially, you shape the floor to make the air underneath the car speed up dramatically. Faster air means lower pressure, and that low pressure zone literally sucks the car down onto the track. Huge grip.
Okay, hold on. If it was banned, surely it was dangerous. I remember those old clips, cars literally getting airborne. Why bring it back?
Yeah, that's the key question. The difference now is the tools they have. Modern ground effect is designed using incredibly powerful computational fluid dynamics, CFD. They can predict and control its behavior way more accurately than back in the day. Plus, there's a really important side benefit for the racing itself.
Which is?
This new generation of ground effect floors produces much less turbulent air behind the car. Less dirty air, as they call it.
So cars can follow each other more closely without losing all their own downforce.
Precisely. Which means more potential for overtaking, closer wheel-to-wheel action. Better racing, basically. It's a clever bit of rulemaking, balancing speed, safety, and the show.
Okay, that makes sense. Speaking of overtaking tools, we have to mention DRS, the drag reduction system. That flap on the rear wing opens up, gives you maybe 10, 12 miles an hour extra down the straight if you're close enough. Seems simple enough.
The concept is simple, yeah. Open a flap, reduce drag, go faster.
But the engineering behind it, doing that safely at over 200 miles an hour, that must be tricky.
That's where the hidden complexity is. That flap actuator. It has to snap open, and more importantly, snap closed in milliseconds. Like blink and you miss its speed. Because imagine braking for a corner at top speed.
Right.
You need maximum downforce instantly.
Right.
So the system has multiple fail-safes. The instant the driver even touches the brakes, that wing has to slam shut. No hesitation. If it failed open while braking, well, catastrophic loss of grip. It's a tiny component doing a massive job.
Incredible precision. And that precision, that detail, it feeds into the whole design race, doesn't it? This balance between testing things physically and testing them virtually.
Absolutely. Wind tunnel time is super restricted now. Top teams might only get, 800 hours a year? It sounds like a lot, but in F1 terms, it's tight.
So they have to rely more and more on the simulations, the virtual world. It's exactly. CFD is king. Computational fluid dynamics. We're talking supercomputer clusters. Running simulations with billions of data points, modeling airflows in ways you just couldn't physically measure easily. And the really good teams, they can get their virtual CFD results to match what the car actually does on track with, like over 95% accuracy.
95% correlation.
Yeah.
Virtual to real?
Yeah.
That's staggering. It just shows how much development happens on screen now before they even build a part. Okay, that focus on efficiency, on simulation, it leads perfectly into the power units. The shift to these turbo hybrids after 2014, that was maybe the biggest shakeup ever in F1 tech, right? Suddenly using 35% less fuel per race.
Huge change. And the efficiency numbers are, as we said, just wild. That little 1.6-liter V6 internal combustion engine part, hitting over 50% thermal efficiency. Your average road car, maybe 30%, 35% on a good day. They've pushed combustion tech to its absolute limit.
So how do they actually do that? It's not just the engine, it's the hybrid bits working together, isn't it?
Totally. It's the integration. You've got two main electric motor generator units, the MGUs. There's the MGU-K that recovers kinetic energy when the driver brakes. Like regenerative braking in an EV or hybrid, but on steroids, it can deploy about 160 horsepower electrical.
Okay, standard hybrid stuff, just more powerful. But the MGU-H, that's the really clever bit, the F1 secret sauce.
That's the one. The MGU-H is connected to the turbocharger. It recovers energy not from braking, but from waste heat in the exhaust gas. So it's harvesting energy others just throw away. But it does more than just generate electricity. By precisely controlling the turbo's speed, using that electric motor, it completely eliminates turbo lag. You get instant throttle response, which drivers love.
Right.
And get this, it spins at over 100,000 RPM. The material science to handle those speeds and the heat from the exhaust. It's incredible. Ceramic bearings, exotic alloys.
Wow.
Aerospace stuff.
Wow. Okay. That efficiency is amazing, but it did lead to that whole debate, didn't it? The sound versus the performance. People missed the screaming V10s and V8s.
Yeah, the sound definitely changed. But F1 seems to be tackling that head on with the next set of rules for 2026.
Right. They're trying to find that balance. Keep the hybrid tech because it's relevant, but make it sound, well, better. And they're boosting the electrical power massively. A 350 kilowatt electric motor that's nearly 470 horsepower just from the electric side. 3 times what they have now.
And significantly, they're mandating 100% sustainable fuels. Net zero carbon, made either through carbon capture or from non-food sources like waste biomass.
So F1 is positioning itself as a leader in that sustainable tech transition too.
It has to, really. But managing all that complexity, the engine, the bigger battery, the sustainable fuel, it all comes down to one thing: data. The amount of information flying around modern F1 is just astronomical.
Yeah, the cars aren't just cars anymore. They're rolling data centers. What was the figure? Over 1.5 million data points.
Yeah.
Every second.
Per car, yeah. Coming from more than 300 sensors measuring everything imaginable. Tire pressures, temperatures, suspension loads, engine parameters, even driver biometrics like heart rate.
1.5 million signals a second. What on earth do they do with all that in real time? It sounds like overload.
It feeds straight back to the pit wall, and often to a mission control center back at the factory too. And it fuels the strategy computers, the pit wall these days. It's less about guys looking at stopwatches and more like a tech command hub. They run thousands of complex simulations, Monte Carlo simulations every second, constantly updating probabilities.
Simulations for what?
For strategy. What's the optimal lap to pit? Which tire compound is best? How much fuel do we really need? It accounts for weather changes, safety cars, what competitors are doing. It's this blend of expert human strategists interpreting outputs from incredibly powerful computers. Decisions are made based on probabilities calculated milliseconds before the car even turns into the pit lane.
So the race can be won or lost right there in the data stream.
Often, yes. And it's not just race strategy, it's driver performance too.
Oh, so how does data make a driver faster?
Every single thing the driver does, tiny steering adjustments, how they apply the brakes when they hit the throttle, it's all logged every millisecond. Then engineers compare that data to theoretical optimal models or even to their teammates' data. They can say, look, you're losing 1/10 of a second here because your brake pressure peaks slightly too late. It's objective feedback. It helps even the most naturally gifted drivers find those tiny, almost imperceptible areas to improve. So you get this fusion, raw talent, refined by data.
Amazing. Okay, let's shift gears a bit from pure speed and data to maybe the most important area.
Safety. Absolutely vital. And honestly, S1's biggest tech wins aren't just lap times. They're measured in lives saved. There's been a fundamental shift from just reacting to crashes to actively preventing injury.
The halo is probably the most obvious symbol of that, right? That titanium structure over the cockpit.
Definitely. Introduced in 2018, it faced some criticism initially for aesthetics, but nobody argues now. It's about 7 kilograms of titanium, but it can withstand something like 12 tons of force, 12,000 kilos.
Incredible strength to weight.
And it's already proven its worth in multiple scary incidents. Now you see it mandated in almost all single-seater racing. That tech transfer saves lives down the ladder, too.
Beyond the halo, the whole car structure is basically a survival cell, isn't it?
Oh, completely. They use aerospace techniques, carbon fiber composites laid up in incredibly specific ways. The idea is for the crash structures, the nose cone, the side pods, the rear, to fail predictably, to crumple and absorb enormous amounts of energy in a controlled way during an impact. That's how drivers can walk away from crashes that register over 50 Gs of deceleration, forces that would otherwise be unsurvivable.
50 Gs. Just incredible engineering.
And sometimes it's the simpler things, too, like the HNSS device head and neck support.
Right, the collar device they wear.
Yeah, just a carbon fiber structure that rests on the shoulders. But it stops the head whipping forward violently relative to the body in a crash. It prevents those basilar skull fractures that sadly claimed lives in the past. A relatively simple concept, massive safety impact.
And there are software safety systems, too, like the virtual safety car.
Yes, the VSC. It's a clever digital solution. Instead of deploying the actual safety car for every minor incident on track, race control can activate the VSC. It electronically limits all the cars to a much slower delta time, maybe 30 or 40% slower than race pace. It keeps everyone safe while marshals work, but crucially, it maintains the time gaps between the cars. So it doesn't artificially bunch up the field like a full safety car can. It's smarter, less disruptive.
All this depends on incredible precision in making the cars, too, doesn't it? The materials science must be nuts.
Absolutely phenomenal. They control the thickness of carbon fiber layers, the laminates, down to hundredths of a millimeter. But maybe the biggest revolution in actually making the parts recently has been 3D printing, additive manufacturing.
How's that changed things? Faster prototyping?
Massively faster. Teams can design a new winglet or floor modification in CFD, 3D print, a version maybe in advanced polymers or even metals, and have it on the car for testing incredibly quickly. Days, sometimes. And get this, the analysis we saw mentioned, teams can even manufacture certain updated parts at the racetrack using 3D printers they bring with them.
Wow, printing parts between sessions.
Yeah, maybe a slightly revised brake duct or a small aero piece. It allows them to react almost instantly if they discover an issue or an opportunity. It's helped level the playing field a bit too, making rapid iteration more accessible.
Okay, so we've covered the extreme tech on the track. Now, the payoff for the rest of us. How does this F1 wizardry actually end up in the car I drive? Is the link real?
Oh, it's absolutely real and probably more direct now than it's ever been, especially with hybrids and EVs becoming mainstream. Think about those F1 hybrid systems, the MGUs, developing those super efficient, power-dense electric motors and the power electronics to control them. F1 pushed efficiencies over 98%. That know-how, those designs, directly inform the motors and inverters in today's hybrid and electric road cars. Same for battery thermal management. Keeping batteries cool under extreme load is vital in F1 and vital in your EV.
Makes sense. And safety, too, presumably.
Hugely important legacy. Those early F1 traction control systems, the anti-lock braking systems they experimented with, they required sophisticated sensors and complex control algorithms. Those very systems, refined over decades, are the direct ancestors of the ABS, traction control, and electronic stability control, ESC, that are standard on virtually every car sold today.
Systems we just take for granted, but they started in F1.
Absolutely. And those systems save thousands of lives on public roads every single year. That's arguably F1's most significant contribution.
You also see it in things maybe we don't think about as much, like the driver interface.
Good point. Paddle shift gearboxes seem completely normal now, right? On sports cars, even regular automatics. But they really trace their popularization back to Ferrari's F1 team in the late 1980s. That semi-automatic paddle shift was revolutionary then. Now it's led to the super-fast dual-clutch transmissions, DCTs, in many performance cars.
So when you really step back and look at it, F1 is this incredible convergence, isn't it? It's like aerospace engineering meets supercomputing meets material science, all focused on making a car go faster, more efficiently, and more safely. That 50% thermal efficiency still blows my mind.
It is a unique technological pressure cooker, and it just keeps accelerating. We mentioned how much development is virtual now, maybe 80% for some teams, which leads to a really interesting, maybe slightly unsettling thought for the future. A final thing for you, the listener, to consider. We know machine learning and AI are getting exponentially better at predictive modeling. What happens when the line between digital simulation and real-time control completely vanishes? Imagine an F1 car using advanced AI, not just for pre-race strategy, but to actively adapt its own performance during the race, changing its aerodynamic setup slightly, tweaking energy deployment, maybe even adjusting suspension settings corner by corner,
all in real time, based not just on track conditions, but on predicting what the car ahead or behind is about to do.
Cars that think and adapt instantly during the race.
Wow. That can be the next technological battleground. Completely unseen, fought in lines of code and algorithms at millisecond speeds. Something to think about.
Fascinating and slightly terrifying thought to end on. Thank you for joining us on this deep dive into the incredible technology underpinning Formula One. Hopefully the next time you watch a Grand Prix, you'll see it with slightly different eyes. There's so much happening beneath the surface.